I would like to introduce Lee Howard, who will be presenting the tutorial on IPv6 familiarity training. Lee has 30 years of networking experience and has presented many times on IPv4 and IPv6 and the transition. He's currently at IPv4.global by Hilco Streambank, and he's one of my favorite people here. So, Lee.
Thank you, Adair. I guess I don't need both mics. For the team in the back, I'm seeing presenter notes on the screen, and there's nothing secret there. But if you can turn off the layer that includes the presenter notes, that might make it easier for people to see all the stuff that's going on here. So you might be wondering why the guy from IPv4.global, why the IPv4 guy is presenting on IPv6. The real question is why the IPv6 guy is working at an IPv4 company. So I was on the ARIN board in the early 2000s, and we were talking about how to promote IPv6. We could see that we were going to run out. What are we going to do about it? IPv6 was one of the topics that always came up. And that's when I really started thinking about it and started paying attention. And then a few years later, I was at Time Warner Cable, and I was starting to, I was in charge of developing technologies. What's the new stuff that we need to deploy in the next couple of years? Let's make sure it's ready for us. And in that role, I started going to the IETF and participating in some of the V6 best practices. I co-chaired 6 Renum, which is about how to renumber IPv6 networks easily. I co-chaired the V6 operations working group, which was very rewarding. Very glad I did that. And then I led the V6 deployment and rollout at Time Warner Cable. So I've been, and then once I left that company, I started a company working on translators. How do we translate between V4 and V6? Because I felt like that was sort of the next generation that was not being adequately addressed. It turns out V6 is too easy. There's not a whole lot of money in the V6 transition. So I moved on. And I also felt like the translation, which is part of the presentation today, but the translation is actually, it's a little bit complicated, but once you sort of spend a couple of hours looking at, all right, what are my alternatives here? Bring it into a lab, spend a day or two testing, decisions made. It's really not that hard. Biggest takeaway today is V6 is not that hard. It's not that scary. The hardest part is getting over the letters and the colons, and whether a 64 is big or small or 48 is big or small. We're used to /27s and /18s, so we're not kind of used to that. So I'm going to spend a little extra time on the real fundamentals there, and then sort of touch on the other things. I can't possibly teach everything there is to know about IPv6 in 2 hours. That's not my goal, and that's why I call this familiarity. My goal today is that in 2 hours, you'll have heard the concepts well enough, you'll understand them well enough, that when you go back home and you start reading documentation about deploying on whatever equipment you have, whatever kind of network you have, that you'll say, oh, I remember this one, I saw this in the training, and it's no longer alienating, it's no longer foreign to me. From that, though, let me kind of get a sense for how many people in the room have actually deployed V6 on a production device by hands. Okay, you guys are going to be really bored for the first 40 minutes or so. Hopefully after that, we'll get into things where you go, okay, now I'm seeing some stuff about security I hadn't thought about, or transition mechanisms, or other sort of more advanced stuff. So it's going to be a breadth of coverage here. I do have a timeline. Actually, I'm going to try and start my clock. I've got a countdown timer, but I also want to see a count up timer because that's how I counted my my slide math here. So I'm going to talk about addressing first, obviously. I'm going to try and convince you that subnetting in V6 is easier than subnetting in V4. People always say, what, that can't possibly, it's too many digits. Let me show you. I'll also talk about, one of the other objections I hear is, how will I ever remember a V6 address? It's just too long. I'll show you. We'll talk about planning, which is another place where people get a little bit stuck. Don't worry about it. It's no harder than V4. And then we'll get into some of the actual protocol mechanics. And this is where people say, I need training on V6. I can't get started. I don't understand. And my goal here is not to drill everything into you. It's to show you, you know what? Learning the protocols that are unique to V6 is no harder than learning any other protocol you had to learn. If you had to read documentation or an RFC or a book to learn how to configure OSPF, you're not going to be afraid of V6. It's not hard. If the differences between Java and JavaScript are bigger than the differences between IPv4 and IPv6. We'll talk about security and how there isn't any additional security in v6 over v4, but also it's no less secure. It's in some ways a little differently secure. And then we'll get into potentially how to get past IPv4 and into a v6 only or v6 mostly network. So I just kind of did that, but I just want to show that's the itinerary. I just want to show you sort of where we are right now, addressing. So it's 128 bits. That was the goal of IPv6, was we're going to run out of addresses in v4. Let's come up with a new protocol where we won't run out of addresses. But one of the questions then is, we're used to dotted quad, right? 1.2.3.4. How are we going to do that with 128 bits? If you tried to write it all out in dotted decimal, it's a really, really long number. 340 trillion addresses is a lot of addresses, and that kind of notation just became cumbersome to sort of think about and talk about. There was another consideration, which was we may not even want to use dots. We may want to be able to embed an IPv4 address syntactically in an IPv6 address. And how would we know that which part is the v4 and which is the v6, which is the embedded IPv4? And so there's an example down there where we've got there's a couple of examples there. The first one on the bottom in the blue section is 2001:0DBH:123456788:90AB:0000:0001/64. So that's, again, it's still a lot of digits. So we've compressed it. We've got a couple of tricks for how to make it a little bit easier to read. So the first trick is any place where between two colons where the first digit is a 0, you can just drop the 0 as a shorthand. It's syntactically the same. Any parser will understand that's what you're doing. You can't drop the trailing 0. You can only drop the leading 0, because if you can drop any other 0, then how would the parser know which 0 to pad back in? So 2001:DB8 is the official documentation prefix. So you'll see that a lot, 2001:DB8. You'll see it over and over and over. You know there's a leading 0. It's 2001:0DB8. Then the other trick for shortening addresses is any place you have a sequence of zeros, a lot of zeros in a row, you can just do : and you can pad those extra zeros. Now, you can only do that once in an address. So if you had 2001:DB8:000:9ABC:000:000:000, you can't do 2 double colons, because again, how would you figure out how many zeros to pad back in those 2 sections? So once in an address, you can do double colon, and you can drop leading zeros. One more thing, as you're starting to look at how do I read an address, is the stuff in orange on the bottom here is the /64. That's the prefix. So just like in cite and IPv4, you've got a prefix, and you've got your network range, and you've got your host bits. The prefix here is the /64. You'll notice it's nice. It's a nice, comfortable 4 sections. There's still debate about what we call those sections of an address. Is it a chomp? Is it a double byte? Is it a hexa? We're talking about another idea. So it's each of those sections is of 4 sections is a /64, and I'm going to show you a few more examples of that. By the way, one more thing is I tend to talk a little bit fast. I tend to get excited, and I tend to really want to run things and be high energy. Please jump up at any time and say, can you say that again, or can you slow that down? I missed it. I would much rather spend, especially right here in the beginning, I'd much rather spend a lot more time going over it and explaining what the heck I meant and what I was trying to say than lose you completely and come back later and say, I just don't understand how we got here. So please jump up at any time, and I'll keep an eye on the mic, and we'll go into depth. So, talked a little bit about the address. The subnetting mechanism. So subnetting is the same in v6 and v4. You've got a slash and then the number of bits used for the network range. So 64 bits, I talked about a minute ago, out of 128, obviously that's half. So you've got 4 sections and then 4 sections. 4 sections in the /64, 4 sections for the network range, and 4 sections for the host bits. That's, again, it sort of seems a little bit confusing for how many bits are used where, especially if you're just starting out with this. So we've got a couple more examples of a 2001:16, Well, it's just a /16, right? How many, how many bits are in the /16 prefix? 65,536. It's 2 to the 16th, just like an IPv4. If you're not used to doing that in IPv4, don't worry about it. You don't need to do it in IPv6 either. 32 bits, you're going to see a pattern here, right? You can see that the first section of addresses, 2001::, is a 16. 2001:DB8, that looks like a /32. 2001:DB8:1234::/48. You're seeing the pattern, 16, 32, 48, 64, starts to begin to be a recognizable pattern that as you're looking at IPv6 addresses over and over, as you're doing subnetting, this becomes intuitive. It becomes obvious where you're just counting how many colons are there in some cases to figure out how many, what the length of the prefix is, what the length of the block is. And then the last example, of course, is an individual address. So that's a /128. There's one address, it's 128 bits, it's a /128. And again, I've sort of color-coded the orange to mean that's the network prefix, and the blue to mean those are the host bits. We okay so far? A lot of people here have already done this, so this is a little bit of review. So when you're doing subnetting, you're going to see things like, so I've got this 2001:DB8, 1, 2, 3, 4, 5, 6, 7, 8, etc. And that's a /64. There are a couple of different ways to derive an address. You're going to see some of these things over and over. But it's pretty easy to look at if 2001:DB8, 1, 2, 3, 4, 5, 6, 7, 8 /64, and the rest of that is 1::1 is one address. 2001:DB8, 1, 2, 3, 4, 5, 6, 7, 9, rest of the address /64. Are those two addresses in the same subnet? It's pretty easy to see that 5678 and 5679 are different /64s. No, they're not in the same subnet. 567A and 5678 are in different subnets. They're different /64s. It's just a number, it's just that last digit. If you look at that first address, 5678, and that fourth address, 5678, yes, those are in the same /64. Actually, they're the same address. So it's, of course they are. But so figuring out your subnetting is so much easier when each digit becomes meaningful in the subnetting. If you've done subnetting, if you've tried to subnet into /27s and you're trying to count every 32 bits, trying to figure out on the fly whether 192.168.214.179 is in the same /27 as 192.168.214.209, you've got to stop and do some real math in your head. You can't just look at the address and instantly know. Maybe you can, I can't. I've done a lot of subnetting with things like /27s and /19s. So I think it becomes much easier in that way. By the way, no, those two IPv4 addresses are not in the same /27. The /27 boundary would be 192, I think. And so one's in the previous /27 and one's the next /27. I don't have a lot of hands-on activities because it's only 2 hours long, but I wanted to give you a chance to open up a command window, a command prompt on your machine, and type, depending on whether you're on Mac or Linux, you can type ifconfig. On Windows, you type ipconfig, and just see the addresses that are on your device. Now, I've got a couple of examples here, and I'm going to actually use the laser pointer to point at them. So you'll see in this case, the MAC address, 6A, 5B, 35, 7D, 3B, BD, is actually embedded in this link local address. Some of this is a little old. Some of these practices aren't universally adopted anymore. But isn't it interesting to see this? So FE80 is a link local prefix. That means it's used for addressing any device that's on the local link. Obviously, it's a link local means. And then we've embedded the MAC address here in the host bits. So we've got 6A, 5B, 35, and then we've stacked in FFFE, 7D, 3B, BD, just like the MAC address. Kind of nifty to be able to see that. And so if you see FFFE in those bits, you're going, aha, I've got the MAC address. This is a, I've forgotten the name for it. This is a OUI 64. So it's a EUI 64, sorry, EUI 64, using the MAC address to embed an address in there. But then we've got two other addresses in here. One is a similar address, prefix length 64, great, autoconf, and the other says prefix length 64, autoconf temporary. So we've got two addresses here. One's a permanent address derived from that MAC address, and the other is a temporary address, so that the real point here is to say, expect to have multiple IPv6 addresses on an interface. That's normal, that's the way it's supposed to work. I've got a link local, I've got a globally unique address, and I've got a globally unique temporary address that might change every 24 hours periodically. And that's the intent there, was to be able to derive an address so that it's harder to track your movement through the internet. So you can't just say an IPv6 address is an identifier that is going to identify you wherever you go on the internet. And of course, the same thing we're seeing over here in the Windows configuration here. I've highlighted the FFFE just in the middle there. It's a little bit easier maybe to read the temporary address and the link local address just because of the way it's formatted. But that's the important takeaway on this one is you're going to have a link local address. You might have multiple globally unique addresses. That's the way it's supposed to work, and that's good. And we're going to talk about in a sec how the device gets those addresses. And so we're going to first let's talk about address planning. So you're building a network, or you've got a network that's running IPv4, and you need to develop your address plan for IPv6. So I've got a couple of design principles. First of all, /64, I really leaned on that when we were talking about the address format. And the reason is that that's a link. If you've got an Ethernet segment or a VLAN or a Wi-Fi SSID, anything that is a single layer 2 link, just give it a /64. Don't try to give it, that's plenty of addresses, and don't try and stretch it out. Don't try and be stingy with IPv6 addresses. You're going to have, generally, the rule of thumb is a /48 per site. The definition of site is a little bit vague, and almost intentionally vague. So you could say a site is a home, a residential user. And IETF recommendations have said /48 per home. That's the way to do it. You've got plenty of addresses here. Some people have been a little bit tighter with that and done 56 or 60. So there's still a lot of addresses there. But it might also be a campus building, a location, a single, an office. A site it's what you think of as being a site. If you need more, that's fine. Because you should be designing for the largest site or network in your network, and then duplicating that regionally. So if you've got a POP or a regional distribution point or a hub or even a data center, pick the biggest one that you have, design your network for that, and then replicate that address plan for every other POP in your network. Because that way it's going to be much simpler to do addressing throughout your network, and it's going to make your life simpler down the road, and you won't run out of addresses. And that's key. There's no reason to run out of addresses in IPv6 if you do your planning. Most important thing is don't try to be efficient. I'm going to come back to that in just a minute, because there are plenty of addresses in IPv6. And okay, quick thing is when you're doing point-to-point links, assign a /64, reserve a /64 because it is one network segment, right? So reserve a /64 for that, but then only configure a /127 net mask. So you've got just essentially like it would be a /31 kind of net mask, so just the two addresses. And I'll get back to, for security reasons, why we want to do it that way. There's no reason to be stingy with addresses. You're not going to save any money. Look, the prices for large blocks of address are pretty darn low. ARIN in particular, an enterprise, so one site is 250 addresses. An LIR or ISP, it's addresses. It's $250 or $1,000 for a /32. How much? What are you trying to save? Why are you trying to be conservative? RIPE NCC, like all of the RIRs, have very low fees for pretty darn large blocks of addresses. If you run a network that is global in scope, that has millions or tens of millions of users, don't try and stick it into a /32. Build an address plan from the bottom up, figure out your largest POP, your largest region, replicate that, and build that into a larger address plan, and go ask ARIN for a /26 if you need it, or a /24, or a /12 if that's what it takes to never run out of addresses and to have an address plan that makes sense. That's fine. There's no reason to be stingy. I'll come back in a second with a thought experiment. When at designing your address plan, try and allocate on the nibble boundary. Okay, what's a nibble? A bit, somewhere between a bit and a byte is a nibble, right? A bit is one or zero, one digit, one binary digit. A byte is 8, so a nibble is 4. So the nibble boundaries are the CIDR notation sizes that are divisible by 4. A 64, a 60, a 56, a 48, a 32. Those are nibble boundaries. And those are, in fact, the trailing digits. It's pretty nifty to look at 2001:DB8, 1, 2, 3, 4, 5, 6, 7, 8, :/64, and see :60, /60 is 5680, and /56 is 5600, and /52 is 5000, and /48 is : : So each divisible by 4 CIDR notation prefix number is another digit in the IPv6 address. That makes it really easy to go and do clever syntactical things with your addresses, because you can start to say each digit is representative of something. I like to use digits to mean some kind of significator. Since I've got so many addresses in such a large network to play with, I like to do things like, if I'm designing a campus network, I might assign 5671, or I might even assign 2001:DB8:1234:1 as the student Wi-Fi network. And 11 might be student Wi-Fi network in building 1. Actually, I'd probably do 101 for the student Wi-Fi network in building 1, because I might have 110 for the student Wi-Fi network in building 10. Or if you're really happy with hexadecimal, you might say 10A is building 10. If that works for you, you can do it that way. I like using significators that way, because then all I have to remember is the prefix and what the heck I was thinking about. So that might be pop 20 in region 2 is 220, and then I've got in my host bits, something means link local on such and such interface. You can start to play with the digits in clever ways that make your life easier. So when you're doing a trace route, or when you're trying to find, hey, something's dying at this address, you can say, I know what that means because I know what the significance of each of those digits is. The other thing you can do instead of using location is you could use security policy. So if my accounting system is on a VLAN that stretches throughout the network, then maybe I pick a digit to mean this is the accounting network, or this might be your management network. Pick a digit, 9 or F or something, somewhere in that prefix. Use that as your management network, and then you can filter on that and write your security policies, your ACLs, your firewall rules, looking just for that digit, and it's much easier to say, oh, this is the management network, and it makes your security policies easier, and therefore, shorter security policy, more secure network, right? It's easier to see what the policies mean. I'm not going to go through an address planning exercise. There are lots of them. ARIN actually in particular has a couple of pretty good tutorials on this, so you can go look at that. I did want to spend one more second on, let me go back, on this one, on not being stingy on addresses, is think about, here's a thought experiment, here's an exercise for you. What would you have to do to run out of addresses? How many networks would there have to be of what size in order to run out of IPv6 addresses? If you start with a /64 per LAN or even per device, how inefficient would you have to be in order for us to actually run into a problem? I did an experiment, thought experiments, a few years ago, and I said, well, what if we did something crazy, like we assigned every UPC code, right? Every barcode on device in a store had a /64, and every single thing sold had a unique serial number that was a host address. And I was trying to be as crazy as I could, and it's still the tightest that I could come up with was that it would take us 200 years to run out of IPv6 addresses. That's probably enough time. Maybe I'm being short-sighted, but I also think that was an unrealistic experiment that I was doing there. So I don't see any reason to be stingy. Good. Getting an IP address. This is where we're starting to talk about the protocol mechanics here. The neighbor discovery protocol is it's how you compare a hardware address to an IPv6 address. This is, if you're thinking IPv4, this is like ARP, the Address Resolution Protocol, but it's different in a couple of ways. So I've got two devices here. Move over to this side for a little while. So I've got two devices here. On the left, I have a device that is saying, hello, FF02::1. That's a well-known all nodes multicast address in a v6 network. So hello to the multicast network. I'm this link local address, FE80::FEDBC, so the rest is host bits. What is the MAC address of this IPv6 address? That seems like a fairly, it's a mechanism we understand. I have this IPv6 address. I need to know the hardware address so I can do direct forwarding. And so I've got a responder over here who says, oh, hello, FE80, because you said you're FE80::FEDBC. I'm this IP address at this hardware address. So this is how we do neighbor discovery. Simple, there's a protocol that defines how that message goes out, what you do when you see that message, and then how to respond back. One of the thing that I think is really cool about that is that we extended that neighbor discovery protocol in order to do, provide information about a prefix. So now I've got a router on this network saying, hello, all nodes multicast. I'm FE80 blank, and I'm a router for 2001:DB8:1234::/64. 3 colons, that's obviously a typo. So I'm a router for this /64. So then every device in there says, I now have a route for this /64. I know how to get there. Next thing you can do is you can do stateless address auto configuration. If you're this host, you can say, oh great, I've just learned this prefix and I can dynamically assign my own IP address within that prefix. Any address within that prefix. So now you go advertise yourself, hey, I've just assigned myself this address, and you go advertise that to the rest of the network. That's really nifty. Within this router announcement, the router can also provide additional information, such as, please don't use SLAAC, use DHCP v6, here's the address. Here's the DNS server that you should use for as a resolver, or other prefix information you can be provided in that, which is pretty nifty, including, here's your default route. That's pretty helpful. So if you were to say, please use DHCP v6, similar kind of mechanism, here's a router that's maybe a home network saying to its upstream, hello, all nodes multicast. Actually, this is not the all nodes multicast. This is the all DHCP relays and servers multicast address. So, hello DHCP server, I have a prefix that I would like to renew. Sounds just like IPv4, except it's a prefix. In this case, it's, I've got a /56, please renew it for me. And of course, the server is going to say, absolutely, you're welcome to do that. If you didn't know your prefix, if you were coming online, if that router was coming online for the first time, it might just say, hello, I'm looking for a DHCP server. Is there one out there? Please give me a prefix. And if you knew that you wanted a specific size prefix, a /64, /56, maybe a /48, you could even say, hello, I would like to renew prefix blank, /64. It's a hint. And the server would say, if it's, or /48. And the server might say, oh, you want a /48? Fine, I have /48s reserved. Here you go, here's one for you. There are a couple of different ways that servers can identify who's requesting. So we've got DHCP unique identifiers. We've got, you can do it in hardware, similar kinds of things to IPv4. So it's not magic, it's just a little bit different. The best part is these two things can go together. So this router that's discovering its prefix over IPv6 can then hand out addresses inside the home using SLAAC. Or actually, it's announcing its prefix, and the devices are automatically generating their addresses using SLAAC. So they work together in a pretty seamless way. And of course, you can also say, similarly, don't use SLAAC, please use this DHCP address. And I'm going to talk a little bit more about why you might want to use one or the other when I get into security in just a minute. Oh, good. I'm actually running a little bit ahead. Not surprised because I talk fast. Checking in, does anybody want me to touch on anything on address planning or address mechanisms or even router advertisements, neighbor discovery? I can do more. Yes. Would you like to use a mic so that people remotely can hear you? Thank you.
Oh, they're there. Thanks, Doug Kaveen, CCSI. So when they auto assign, how do they not interfere with one another?
How do they not collide? Actually, so you're right. I didn't get into that. So once you've said that, that's part of what you're doing here with the telling the all nodes multicast address, hey, I've just chosen this address on this network. I am now 2001:DB81234:123456 FFFE 7898ABC. That lets every other device on the network, excuse me, know that there's a neighbor here with this address. It's called DAD, duplicate address detection. And so other devices on the network now have a chance to say, no, you're not. That can't be you. I'm already that address. And so then there is a pretty simple mechanism to say, oh, all right, I've got another 18 billion addresses, billion addresses to choose from. I'll go just pick a different address. Obviously, maybe not obviously, but in the case where you're using your hardware address, the EUI 64, so the MAC address, as your host bits, very unlikely to have a collision there, an address collision. But then again, if you're doing random assignment in 18 billion addresses, also pretty unlikely to have a collision. There are cases where that could happen. Lots of times people do things like try to say, well, I always want to make sure that this device has ::1. It's a well-known address, it's easy to remember, but you may have multiple people saying, I want to be ::1. So there's a mechanism there, but if you're just doing, if there's enough entropy in a network, it's going to be random enough to make sense. Perfect question. All right, I'm going to talk a little bit about security, and as I go, this is a good time to say, wait a minute, you said earlier, or dig in. Actually, Warren promised he'd push hard on the stuff that I may be a little bit vague on, because I don't spend all of my time in security. And so while I understand the protocols, I don't necessarily think all the time about how to, about the potential vulnerabilities or attack surfaces created here, and then so I don't think about the mitigations necessarily. So I'm going to try and, again, go a little bit slowly and make sure that this is a good way to, that I'm spending enough time to try and at least make you familiar with where the attack surface is. So when you go read documentation, you can find what you need in order to make sure your network is secure. One of the big objections that I hear people saying about IPv6 is, but there's no NAT in IPv6. I need NAT because I need my security. I'm delighted to hear people chuckle at that because it drives me bats. So there is a little bit of arguable security in a NAT, and I'll show you why it's not nearly as secure as you may think it is. So we're back in IPv4 land. So this is ancient history. So we're back into the history of IPv4, and I've got a device on the left that's going to reach out to a web server. That's the thing on top there. And so here's a packet. That computer on the bottom there has an internal source address, 192.168.1.4. And it just picks an internal port number, a layer 4 TCP port number. And it's going out to the web server, which has address 192.0.2.80. And it's going to 443, which is the well-known TCP port for HTTPS. So it sends that packet up to that router. That router, though, being a typical home router, only has one public IPv4 address on its outside. So it has to rewrite that packet, right? So it rewrites that packet to say, okay, my source address is now my outside address, that public address. So my source address is now 192.0.2.133. I'm picking port 4765. I'm still going to the same destination though. So I've only rewritten the source port. Okay, so that packet now goes out to that web server, and the web server sends the packet back, and the router will translate it back. It's got a state table. It's building a table that says if I receive a packet on address 192.0.2.133 port 4675, I know that I need to forward that to my internal address, the device with internal address 192.168.1.4 port 2385. So that's in NAT or in IPv4, that's a 5-tuple. And so we're mapping that 5-tuple to say, if I've got this source and destination and port number and these ports, that's the state table that I'm creating to do the translation. The trouble is that if you're trying to set up a game, multiplayer game, then you may have people who are trying to talk to each other in order to shoot each other or whatever they're doing in the game. So that server might say, hey, device B over there in a completely different home, completely different part of the network or the world, go talk to the other gamer on 192.0.133 port 4765. Remember, that's not the address of device A. That's the address of the router outside of device A that's providing this address translation. And so it's going to have, so it'll say, go talk to that. B will therefore send a packet sourced from its own self. Now, of course, in this case, B has a private address. The router router B is also doing address translation. So that router B is using its outside address, 192.0.2.229, picking a random port, 2781, sending traffic over to 192.0.2.133, port 4765, which is the outside of the router on router A. Router A receives that and says, okay, I've just received a packet, source 192.0.2.133, 476, and it says, now wait a minute, I have a state table that maps 192.0.2.133, 4765, and 192.0.2.80, port 443. I know that 5-tuple. I know that I should map that. But I also know that, so normally if this were an actual firewall, it would say that 5-tuple doesn't match, the packet on the right does not match the rule on the left, I'm going to drop that packet. But if I'm trying to open this up so that gaming can happen, I'm doing a full cone. As soon as there's any traffic outbound on port 4765, I'm going to allow anything inbound from port 4765. So once I've created a connection anywhere on the internet, I now set up a rule using a much smaller tuple, the 3-tuple of 192.0.2.133. If I receive anything to that address, to port 4765, I'm going to forward that to device A, 192.168.1.4, port 2385, which was the original port that I chose. That means that if you have a connection anywhere on the internet and somebody sends packets to that address and port number on the outside of that router, it's going to get forwarded to your device. So maybe that's a little bit more secure than just allowing all packets to that address. But if it's all packets to that address and port number, it's not a lot more secure. It's only a little bit more secure. And so it's now completely open to the internet. And this is how most NATs are set up. Not all, especially in an enterprise IT situation, you might have done it, so it's using the 5-tuple to build that state rule, but most people that I talk to don't actually know which way they have it configured. Every time that I've done configured NAT in an enterprise scenario, I've looked at recipes and I've said, there are 5 different ways to configure this on my device, and I don't understand the difference between them because the documentation really isn't clear. So I just worry about NAT as any kind of security. It's not there. You need a firewall. If you're going to try and protect inbound packets, you just need to have a firewall, and NAT isn't it. People do think that IPv6 is more secure because there's so many bits you can't possibly do host scanning, which is somewhat true. You've got, as I pointed out earlier, you've got 18 quintillion possible addresses in each /64. That's a lot of addresses. And if you're randomly assigning addresses using SLAAC in that /64, 1 in 18 quintillion, that's a lot of hosts to have to send a ping packet to in order to discover what's actually active out there. And in fact, if you're sending that many pings, you're already doing a DOS attack. And by the time you've gotten through 18 quintillion possible IP addresses, whatever device you were trying to find may have reassigned itself a new temporary address the next day. And so even if you did ping it, 10 minutes later, it's got a new address. So it does have some improvement there, but I kind of mentioned this earlier. A lot of people will go and use memorable addresses. We'll use : 1 or : 2 or : 80 as a web server, or : 1 to say, oh, it's this router, this interface, or : beef. I like using words. I like saying, dead beef, feed cafe, Cisco had dog food, DO6:F00D. I like that. That's clever stuff. But it's also fairly well known. Leet speak is not actually security. Yeah. And of course, you can embed an IPv4 address in that IPv6 address. I talked about that at the beginning when I was saying why we're using colons and hexadecimal is you might embed an IPv4 address. But that's a much smaller space to have to scan. If you can scan the entire IPv4 space, you can scan the IPv4 space embedded within a /64 in IPv6. Or of course, if you really think that we're still using hardware addresses, you could say, well, I know the top 3 or 10 manufacturers of network interface cards. I know what OUIs they're using to assign MAC addresses. So I can just pick the top 3 or 10 OUIs and scan that space, and it's a much smaller space. I think it is better. I think there's enough address space here that there is some mitigation, but it's not quite as impossible to scan the address space as some people would have you believe. Or not even as some people would have you believe. I suppose I would say that differently, as to say, as it might immediately seem. It's not as hard as it might immediately seem because of these kinds of tricks. So how do you mitigate that? Well, the first thing is have a firewall or an IPS that is either blocking ICMP v6 discovery packets, things that look like scanning. If you see a ping sweep, you can block that. You can rate limit ICMP v6. I'm going to talk about that in a little more detail. Sort of the kinds of things that you would typically do in IPv4 to block ports ping sweeps. Oh, that's right. This is where I was going to talk about it. So you can also configure that firewall or host to drop echo request packets. Maybe you don't want to accept ping and traceroute inbound. You only want to see echo reply. That's fine. That's a perfectly reasonable thing to do to prevent network scanning or reconnaissance. But don't block this packet too big. And I'll talk about the different IPv6, so ICMPv6 types in a few minutes. But the packet too big is how you detect that there's fragmentation in the network. It's how you say, you send out a packet that exceeds the MTU somewhere along the path. You want to get that message back that says, you need to fragment this before you resend it. So that's an issue. You can block that on routers that have lots of different MTUs. So, they can only if you've got an MTU mismatch on a router, you've got 9,000 on one interface and 1,500, you might expect to see to be sending packet too big messages there. Another mitigation, I kind of said this in the last slide, is ignore what I said about using mnemonics for addresses. I like using syntax. I like saying this bit means this building, or this digit means this security zone, but it does make it a little bit easier to say, okay, we've discovered the space here. We can figure out within this syntax what we're using here, and especially if you're talking about POP5, router 2, interface 101. Those, I love using those as host addresses, but it does become, once you've discovered the pattern, it becomes pretty easy to figure out what the pattern is for other routers. Then again, if you're doing the right kinds of ACL and protecting your management network, you're probably doing the right things anyway. And of course, you wouldn't do this on routers, but for hosts, use privacy extensions. That's the change addresses every 24 hours or 10 hours or 1 hour. That in most operating systems, that's configurable if you go looking for it. But that also makes it really a whole lot harder for somebody to scan the address space and find a given address, because by the time they found it, you're changing addresses again. That's pretty straightforward stuff in terms of the kinds of security in ICMP, the basics. Something else that I still hear from time to time is that IPv6 is more secure. This actually comes up more in the press, where some journalist is trying to write an article about the next generation internet protocol and just goes and reads, like, not even the Wikipedia page, but some old article. Or maybe this is because large language learning models are trying to generate articles about IPv6 without actually doing any research. But I still see from time to time people saying IPv6 is more secure because it includes IPsec. In fact, the RFC says that in this section defining IPsec, that defines the management requirements for all IPv6 implementations, and implementations for those IPv4 that do require them. So it's sort of implied that it's optional in IPv4, but required in IPv6. It's mandatory. No, it's not. And you know what? It works. I mean, IPsec, we use it. We know how it works. But it's also, it works just as well in IPv4. And once it was backported, it's no longer any kind of advantage. So you can consider that debunked. Not saying it's a bad thing. I'm just saying it's no better in IPv6 than IPv4. Okay. Neighbor discovery protocol vulnerability. I talked about how a router can send out a router advertisement using the neighbor discovery protocol that says, hello, I am your default router. I'm 2001 DB8::1. What if somebody else says, wait, no, I'm 2001:DB8, 2001:DB8::1. How do you figure out which one is which? Well, honestly, it's the same problem that you have in IPv4, where you might have a rogue DHCP server, right? It's the same, or even a rogue default router saying, here's default, here's this MAC address is this IP address for your default route. No, this MAC address. So it's really the same problem, but we sort of look at it a little bit differently when devices are picking their default router and are configuring their own route, their own addresses out of that prefix. There's also another potential vulnerability in neighbor discovery, that is the cache table exhaustion. This one's a little bit different than an IPv4, so let me sort of, I'm going to come back to that in a minute. Some people, and this is particularly with enterprise IT operators, say, I can't use SLAAC. I can't let a host decide its own address because then I don't have a log of it. I don't know what address they chose, and I need to be able to go back and say, hey, I saw an attack or I saw some kind of weird traffic on this IP address, and I know which device that is. Well, in IPv4, you have the same, and I know in the IPv4, I use DHCP and I assign an address. Well, except I don't know how many people have run a corporate IT network, and I have. You always worry about somebody plugging in a device into the wall and they say, oh, I'm not authorized to get a DHCP address, so I'm just going to configure a manual address that I know is unused right now, and suddenly I'm on the network. So what you're looking for here is how do we prevent that? In IPv4 and IPv6, probably 802.1x is your best solution. Don't rely on MAC address as being an authenticator. That's just like relying on an IP address as an authenticator. It can be configured, it can be changed. Use certificates when you can, and anything that you aren't able to certificate should be untrusted. Maybe you put it in a public access network, maybe you're doing other mitigation, maybe you put it in a network that sets off an alarm in the NOC and somebody has to go running and figure out where that device is. You can also, and this is, I love this ability, and this is something I really suggest everybody do, is look at your switch or your Wi-Fi devices, and when somebody does assign itself an address and says, hi, local network, I'm this IP address at this MAC address, that should be logged. It's a perfectly reasonable thing to log on whatever the layer 2 aggregation device is, switch, Wi-Fi device. And so then you probably want to take that neighbor table and log it back to wherever you keep security logs. Wherever your DHCP server logs are, whatever, log it back there using SNMP or syslog, netconf, whatever you like. The trouble is I've had a hard time on some devices figuring out ways to scrape that information and get it back there. So I'm back to kind of doing screen scraping kinds of, all right, every 30 seconds or minute, I'm going to do a show log, port it back to my server, and then do a diff from what I had before. It's a darn nuisance. But if you really need to know which device assigned itself an address, so that if the cops come knocking, you can say it was this hardware address, that's how you would do it. I'd meant to include a handout, and I'd meant to include a handout that included some further reading and some of the well-known addresses. So I talked about before the well-known addresses, the all nodes address, the all nodes multicast address, the all routers address. Later on, we've got at the bottom is the all DHCP relay agents and servers. So these are sort of the well-known addresses. Part of the fun here is, and we've seen Smurf attacks in IPv4, but you can certainly send packets to and from these addresses, and ideally you've got ACLs that are blocking that, so you're not actually forwarding traffic that's destined for link local sort of contexts. And that's not hard to do. Just anything that starts with FF, actually probably anything that starts with F, don't allow it to be forwarded across your network. That's intended for link local. I mentioned the neighbor table issues. Like this is sort of, and this is a little bit of an oddball where there's a possibility. So here's how this would work. So I've got a device saying, hey, I've got an IP address. I need to know the MAC address. So it sends a neighbor discovery packet. Who is 2001:DB8::1? The switch says, oh, I'm getting this. I've seen a neighbor discovery request. I need to pay attention to this because I need to be, when I receive a packet, I need to know where to forward packets to hardware addresses. So it's going to say, it's going to open this and have an open entry waiting to hear back. Okay, there was a request for 2001:DB8::1. I'm going to wait to hear the MAC address. And so it'll wait some configurable amount, usually configurable amount of time before saying, oh, nobody actually has that address, and it'll wipe out that pending entry. But then you could ask again, well, who has 2001:DB8::2? All right, I create another entry, the neighbor table entry, and I'm waiting to hear the response on that one. And then you can keep going and doing every address from : : 0 to : FFFFFFF. And that's the point where, oh, gee, the switch starts to run out of memory and capacity and bog down. And so that's a potential concern if somebody happened to pop that box, the computer that's there on the right. Concerningly, in some cases, it's possible to do the same thing from outside the network. So you could send to the router or to the local network who is this address using a neighbor discovery packet and potentially exhaust the neighbor table. So that's this is sort of like ARP exhaustion. It can happen, super rare. It's mostly theoretical. I don't know if people, I think I heard of somebody saying this happened once in the wild, and so immediately we started discussing remediations. And so the remediation is to do a couple of things. I'm going to come back to that in a minute because this next attack is pretty much the same thing. Oops, I went backward, I meant to go forward. I just love the name of this attack. It's exactly the same thing, but in this case, you've got a link to a point-to-point link. So two routers connected to each other. One's in 2001:DB8:0:F001: 2, and the other's in the same /64 with : 3. By the way, why did I use 2 and 3 instead of 1 and 2? Well, because 1 and 2, 1 isn't an even number, and so I could go 0 and 1, or I can do 1 and 2. I'll come back to that in a sec. But it's the same exact thing, is I can send a packet to : 3 asking who has : 4 and : 5 and : 6 and : FFFFFFFFF. So it's same thing as those two devices could say, well, I don't know what else is on this network, so their neighbor tables could get exhausted. Easy way to mitigate that one, you reserve the /64, but you configure a /127. So there isn't that infinite space, that 18 quintillion possible addresses on that segment. There are only 2 possible addresses on a /127. Some devices, have been, years ago, had trouble with 127, so maybe you do a 126 or a 124 or something, but a small enough space that you wouldn't be able to exhaust that pending table of neighbor entries. You can also, so that's the easy way. General guidance is reserve a 64 for the point-to-point link, but configure a /127 net mask. You can also put an access control list on any unused space. Don't allow packets destined for anything above : 3, because I know there's nothing else on that network segment. You can rate limit. So this is for both attacks. You can rate limit the neighbor discovery queue. So if you've got, so you can say only allow up to 30 pending neighbor discovery requests at a time. Or if you have different, let's say it here, if you've got different queues for existing entries and pending entries, so I showed earlier, this request is open, I haven't received a response yet. If those are different queues, then rate limit the open ones and allow the existing entries to renew themselves and say, I'm still here, I'm still an active device. You can certainly rate limit IPv6, talked about that a little bit, probably generally a good idea. Sort of depends on the kind of network you're running though, where you would do that. You don't want to do a whole lot of policing of your entire network on your access, on your peering edge. So where in your network do you do this? Good question. You need to think through the policy there and design it for your own network. On an enterprise network, you could probably do that at your firewall edge. And of course, there are lots of different places to log negative NDP entries. And so I sort of talked about syslog and netconf and the other mechanisms there. Every once in a while, as you're doing reading, you'll come across send, secure neighbor discovery. So how do I make sure that my neighbor discovery packets are actually, how do I certificate that? How do I do, is there a PKI equivalent for neighbor discovery? And there sort of is, and it's called send, and it is not broadly supported, and it is kind of hard to configure even when it is, because you've got to have a trusted path from your local layer 2 network up to whatever your certificate authority is. So I mention it so when you see it, you can go, right, probably not going to be able to do that. Pretty much enough said. RA guards, a couple of different ways that you can make sure that the router advertisements, hey, this router is serving /64, this prefix, this /48. There's a couple of different ways that you can make sure, depending on policy, to make sure that only the router that is actually authoritative for that network is receiving traffic. If you can plug in a random router, and again, as an enterprise IT guy, when I would plug in, I was always worried somebody was going to plug in a wireless access point into my network and suddenly be the router, and therefore that's an instant man-in-the-middle attack. So you can make it a couple of different policies or ways to implement that to make sure that you're only taking router advertisements or sending router advertisements from where you want to. You can block RAs from specific MACs or ports on your switch. So for instance, only the port that the router is connected to is allowed to send router advertisements. Probably a good idea. You can allow access to RAs that comply with whatever the policy is. That's sort of where you would apply send, for instance. Or you can use prefix list or prefix range to map the kinds of networks, the access that you're looking for. You can also, if you wanted to do this, you can have your layer 2 switch be a router advertisement proxy. So only that switch will allow RAs, and it will send neighbor discovery to the router, and it will only allow RAs from the router once you've configured that. Again, this is you got to go read the documentation to see how to do this on your specific set of devices, and it's not universally implemented, but it's another way to sort of make sure that only the active router is able to do that. When you look at that, if you do that, you'll notice that the sequence of who is sending router advertisements, where's this coming from, how do I build the table of trusted devices, goes in the state, it goes from off to learning, blocking, and forwarding. That looks like spanning tree, right? That looks very familiar because it kind of is. It kind of is the same thing where you're building a state table of where's the next hop, where's the next path in my sequence, where should I be trusting to forward packets to. Source address verification improvements, Savvy. This is sort of, I think now it's pretty standard security stuff. This is pretty straightforward. How do I make sure that I'm getting packets from places that are legit? How do I make sure that I'm, for instance, not receiving spoofed packets from outside my network? A couple of different ways to implement it. First come, first serve is the easy way to do it. First, the first person who says, I'm using this address or this prefix or whatever is the authorized user. Very simple, creates a state entry, first device up is the winner, and you don't allow router advertisements from any other device in the network. Sends, I talked about it, drop packets where the source is not certified. Using DHCP, you can snoop DHCP packets. So if you're the layer 2 device, you can snoop, and you can say, hey, I'm only seeing DHCP responses from this server out there, so I'm going to set a state table and say that device is trusted. That works, again, that works pretty well because then that device is the one that's trusted, unless somehow some other server gets in there first, then you've got a race condition. But then you wouldn't allow DHCP responses from any other untrusted port on that device. And then you can do some kind of mix there. Again, not really trying to tell you how to configure that one, but thinking about how do I make sure that I'm mitigating my layer 2 concerns, that's where I would, that's another one you should look for. Cisco has talked about how they've implemented their corporate network, and so this might be your management network, your NOC network, your internal networks, and I appreciate that they've talked about that publicly, so here are the techniques that they have specifically said they're using. Not that Cisco is necessarily the most trusted source or the best source, just an example of somebody who said, hey, here's what we did to make sure that we were trying to follow best practices in our network. All right. We have one or two more things on security. This is one that often shocks people, and I've done training before, and I've done consulting and said, let's talk about a couple of things. I didn't want to spend a whole lot of time talking about reasons to deploy IPv6. That's other talks. But one thing that I really want people to be thinking about is if you're not deploying IPv6, but you have a VPN, you might have a policy that says when you're connected to the VPN, so in this case, I've got a home user down here at the bottom, connected to a VPN, and before it goes out to the web or whatever other traffic is doing, my VPN controller firewall is inspecting all the traffic and applying rules to secure that device and make sure it's only doing things that I want to allow it to do. So if it's trying to get to a web server, if this device is connected to VPN, all traffic is going to go through that VPN and then before being forwarded to a web server, and the responses will go back through the VPN for some kind of sanitization. If your VPN controller doesn't know what IPv6 is, or if the VPN client doesn't know what IPv6 is, and the user has IPv6 at home, like most users in the United States do, then as soon as it connects to the VPN, v4 traffic will get forwarded to the VPN controller, and v6 traffic will just go out the internet through the local connection. all of a sudden you've got a split tunnel on your VPN, and you're wide open to whatever else is out there. So at the very least, check your VPN and make sure that you are not inadvertently breaking your own security policy. People panic when I show them that one if they haven't seen that before. So fragmentation, we haven't talked about this a whole lot. In IPv6, I think Jeff mentioned it yesterday, but in IPv6, we're looking at the problems of fragmentation in the middle of the network, and where do you do disassembly and reassembly, and how do you know, especially if you drop a fragment, when do you know, how long do you remember that that you're waiting for a fragment? V6 is a little bit different, where only the endpoint is allowed to fragment. So if you've got a packet that's going to be too big for some place in the middle of the transit path, then that packet is going to get dropped, and whatever device had to drop that packet is going to send back to the source a packet too big message and say that packet was too big. Please send multiple packets. Break it up, fragment it, send multiple packets. And so then we get a fragmentation header that says, hey, this is fragment 1, this is fragment 2, and so on. One of the problems with send is that the router advertisement can actually be too big. So then you've got who might be able to send fragments of an uncertificated, or fragments of a router advertisement, potentially concerning there. A little bit of a corner case. That's a little bit tough to get to. But I have seen cases where there are lots of different prefix information options, PIOs, in that router advertisement. So I want to give you a lot of different information. Maybe it's just, hey, instead of one resolver, I'm going to give you 5 resolvers you might use. Or I'm going to give you some multiple different kinds of, I'm trying to think of other examples, but lots of other information that you might want to use in configuring the device, and then that might have to get fragmented. Mostly this is not a vulnerability, but it is a place to look for if you're having trouble connecting on a local network, this is a pretty good place to say, all right, let's slap Wireshark on there, take a look for it, look for is something being fragmented and we don't have enough information to be able to reassemble it. It's also, the big one though, is fragmentation on the internet someplace. So, hey, I'm trying to send data to some site, some other device, some host someplace, and it's failing, and the packets are, the connection's timing out, or we've got some kind of failure scenario, and I can't figure out what it is. Take a look at, is there some place, are you receiving packet to ICMP, packet to big messages, or are you blocking ICMP someplace, or is ICMP even just being rate limited and being dropped someplace so you're not receiving packet to big messages? That's a place to go troubleshoot and say, okay, maybe I need to set my local MTU to 1500 or 1400 just to make sure that I'm not breaking someplace else. It's one I've seen a few times where there's actually turns out to be a tunnel somewhere in the path, and the tunnel headers take up some of that that packet space, and so even though you're sending a 1500 byte packet, somebody else needs to add tunnel headers, and they also only have a 1500 byte MTU, and so they'll drop it, call it fragmented, send it back, and you say, but I'm already at 1500, I'll shrink it down to 14 or 1200. I kind of hate talking about extension headers. I have to talk about them. It's baked into the IPv6 protocol. When doing the design, the IPv6 designers said, we need to make sure that we allow room for other things to happen. Let's not build a protocol that has no space to ever be changed or adapted to evolve into, to do other things that network users might want it to do. So they created extensions, extension headers. So, and pretty clever way to say, hey, in the IPv6 header, there's a space to say, I've got more information, go look for the next header, and here's what it is. And they created a bunch of them. There's a hop-by-hop header, there's a destination option header, routing header, fragment header. Fragment's pretty important, I just talked about that. The IPsec headers, AHESP, and others. There's other headers, you can see the IANA registry and go look up what the extension headers are. If you have a device that's doing layer 4 or higher inspection, you might want to have it look for the headers. Look for where's the next header. Part of that is you might want to drop headers that you don't know what they are. If you're not using that in your network, maybe somebody else is trying to do something in your network that you don't want them to do. And I've got a quote here. from one RFC pointing to another RFC. Make sure that your ACLs are able to process those extension headers. Let me talk about the best practices. Generally, I advise allow fragment headers because you need to be able to send fragments and receive fragments because there may be packet too big somewhere in the path, and allow IPsec. Generally, probably a reasonable thing to do. If you use the destination option header or the routing header, then allow those. If you don't, then there's probably no reason to allow those. You don't want somebody outside your network injecting destination option headers telling the destination device what to do with that packet when it receives it. That's probably not something you're looking for. And then inbound, you probably don't want somebody outside your network setting hop-by-hop headers, extension headers. You don't want somebody saying, hey, every hop that you get to, parse this header and do this extra action. That's probably not something you're looking for. There's interesting avenues, interesting options for things we could do with that in the future. And in the future, we may say, we've got a great idea for how to do, I don't know, DDoS mitigation or something using extension headers, whether it's destination options or hop by hop. But we probably, in the meantime, if you're not using it, probably just go ahead and block it. Same with mobility headers, host identity protocol. Generally block them unless you know that you're using them and there's a reason to allow them. Just deny unknown, sort of typical security policy. I've talked about ICMPv6 a couple of times. The link local multicast and address discovery, probably need to allow that. I mentioned the multiple address types. In IPv4, a lot of people just block all inbound ICMPv6, right? All ICMP. Because I don't want people doing a reconnaissance attack on my network, ping sweeping everything and figuring out what's on my network and where it is. So you can't just block all ICMPv6 because then you're blocking important things like the packet too big headers, destination unreachables. So I generally say inbound, I want to allow echo reply because it sort of indicates that I'm doing a ping or trace route outbound and I want to see the response. Outbound, I definitely want to allow echo request and maybe echo reply because I want to allow people to ping. But you have to allow the packet too big header is the big one. I sort of feel like no discussion of security is complete without at least mentioning spam. Last I checked, of the top 50 sites, I think I was looking at the United States, but of the top 50 sites, only 22 of them had IPv6 MX records. So fewer than half of the major mail servers in the US are allowing IPv6. And of those 22, 20 of them are actually using Google Mail in some variation. So, great job, Google. They've really built a good product that works and is scalable and supports IPv6. Oh, by the way, just for the record, those two were LinkedIn and Wikimedia. So, not for nothing. And LinkedIn generally has fantastic IPv6 support. Like they have really gone, almost IPv6 only internally. There is a best current operating practices document in progress on how to mitigate spam in IPv6. It may be similar to whitelisting known servers. It may be sort of fuzzy reputational logic. We're sort of still getting there. The problem is that most of the spam mitigation tools that we're used to in IPv4 just don't work in IPv6. In IPv4, if you get spam from an IP address, you say, all right, I'm no longer accepting mail from that IP address, and maybe you go report it to an RBL. But in IPv6, if you block one IP address, well, there's another 18 quintillion addresses in just that one /64. So do you block the whole 64? All right, maybe. But there's another 65,000 addresses in the /48. So do you block the whole 48? Maybe. But maybe that's a different customer. Maybe there's 56s, or maybe it's different 64s in a data center. There's not enough logic. We don't have enough rules there. We don't have enough information to know how big a block we should block. So we're still working on sort of more advanced spam mitigation tools in IPv6. There are some tools that are specific to IPv6, like standard security tools, doing scanning, doing vulnerability analysis, that kind of thing. Most of your tools that you're used to using in security assessment and mitigation are going to now support IPv6, so you can use those. There are a couple that are particularly looking for some of the particular things that I've mentioned already. THC, IPv6 Toolkit, and the FT6 firewall tester are specifically looking for the kinds of v6 specific things that I was just mentioning. So if you're a security person, go take a look at those and figure out what's the best tool for you. I wrote a few years ago in RFC 7381 that running a dual stack network doubles the attack response, the attack exposure. Because now a malevolent person can attack both on IPv4 and IPv6. I'm not sure I still believe that. I don't think it doubles your exposure. I don't think you're doubling your attack surface. Yes, you have two address families, so there's more IP addresses to potentially attack, but there's a lot of ways to secure IPv6, and the security is, again, security in IPv6 isn't harder or worse, it's just a little bit different, and I've gone through everything that I've talked about is the specific things to IPv6. Most of the security things that you worry about in IPv4 also apply to IPv6, not all. We're not as worried about ping sweeps. It's possible, we're not as worried about them, but there's those few specific things. So the takeaways, summary for security here. IPv6 is not more or less secure than IPv4, it's just a little bit different. If you need a firewall, use a firewall. Don't expect NAT to save you because NAT is not a firewall. Rate limit ICMPv6 to mitigate some of those discovery, those table exhaustion attacks. You might want to do that kind of thing elsewhere in your network, but rate limit certain kinds of IPv6, but allow the ones that are critical. Talked about that in that slide. Allow the extension headers that you're using or that your users might legitimately be using, and then block everything else. And if you can, use RA guard, that router advertisement guard, to prevent rogue router advertisements, and use source address validation improvements, use Savvy. Those are pretty simple, and that's sort of my favorite basic 5 bullet points for security in IPv6. We're okay. Does anybody have any questions on anything we've done so far? I'm happy to take questions at the end. I think we're going to have time, but I also want to allow time for people to stop now. Hearing none, continuing on. So, the big problem with IPv6 is that if you just run dual stack, which is what everybody starts off with, you haven't actually solved your IPv4 runout problem, right? If you're using an IPv4 address and an IPv6 address everywhere, you're still using an IPv4 address everywhere. So how do you get past that? How do you get to v6 only? We use transition mechanisms. Transition mechanisms, and we call them transition mechanisms, not translation mechanisms, because not all of them are doing translation. Some of them are doing tunneling. Some of them are doing other kinds of encapsulation or mechanisms that are clever, but not necessarily a literal translation from one address to another. I'm going to talk about, I think, 3 of them. The first one is 464 XLAT. I hear there are a lot of evangelists for 464 XLAT, and they're not wrong. It's pretty solid and it's pretty simple. I'm going to go through it slowly because it's simple once you understand it. It's also, I've heard an argument that I'm sympathetic to, which is a lot of mobile carriers are using 464 XLAT in their mobile networks because there's Android includes a client address translator, a CLAT, in the handset. So you already have the client end. So they're familiar with it, and so they want to port the same thing into their landline networks. So there's some already existing implementations kind of around the world. So here's my scenario. I have a home. I'm an ISP, that's the cloud. I'm an ISP, and I've got a home that I only want to give IPv6 to. I don't have any more IPv4 addresses. I'm only going to give it an IPv6 range, an IPv6 address. But inside the home, there may still be devices like this cute little IoT device. There still may be devices that only speak IPv4. I'm going to jump on a hobby horse for a second and say the laggards, the things holding back v6 deployment, sure, you can blame ISPs in some places, but in a lot of places, it's these consumer electronics devices where they're just grabbing a stack, an embedded OS someplace, grabbing a stack off the internet, making it barely work for the device, and sending it out, and they're not even thinking about IPv6 because no consumer is looking at the back of the box saying, does it support IPv6? They're not making any, there's no difference in revenue or expense for them, so why bother putting it in there? So a lot of consumer electronics, IoT devices only support IPv4. That's why I'm using it as an example. So you've got our cute little guy with eyes here, that's our IoT device. He's only got an IPv4 address inside the home, but he needs to reach something outside the home, like this web server on the left, 203.0.113.33. Okay, I'm gonna do the same kind of, the NAT walkthrough I did before. I'm gonna do the same packet walkthrough in this case. So I'm the IoT device. I've done a lookup on whatever that web server's name is. I've got an IP address that I need to send something to. So I'm gonna send a packet with a source address, the only address I know, 192.168.1.192. Destination address, well, the web server's IPv4 address, 2003.0.113.33. I send that packet to my default gateway, which is the home router. Home router receives that packet, but it knows it only has an IPv6 address on the outside. But it also has the client address translation, the SLAAC. So it'll translate that and say, and it's been configured to know where there's a translator elsewhere in the network. So it says, I'm going to send this packet out with my source address, which is 2001 DB8 2001 1234::29, to a destination address of the XLAT, the translator that's up in the network someplace. And this 64:FF9B is a well-known prefix for NAT64 translators. So that allows you to anycast it if you need to. Come back to the anycast problem in a sec. So I'm going to send this to a destination address of this well-known NAT64 translator. But you notice the address that it's sending to is 64.ff9b: 2003.0.113.33. That's the IPv4 address of the destination web server. So that's going to send that pack. So hey, destination. So the server, the NAT64 server, the XLAT, receives a packet with source address 1234. Okay, that's the home gateway, and destination address, my inside address, my IPv6 prefix, 2003.0.113.33. I can forward that to the proper destination. I'm going to forward it to that web server, 2003.0.113.33, with my outside source address, 192.51.141, which you can see it's configured in the server on the right. So you send that packet to that web server, and it's an IPv4 packet. Darned clever. That means the return packet goes back to the outside address of that NAT64. It says, I've got state here, I know how to do this, and I know where to forward it, so I can forward it back to that home router, and Bob's your uncle. The problem is, let's see, yeah. The problem is that if you're anycasting, if you have redundant servers and you're using this well-known prefix, you hope that the devices are all sending to the same NAT64, the XLAT server, because if not, you don't have the state entry to do the reverse mapping. So it is stateful. It turns out there's lots of hardware that can actually handle significant amount of state for specific cases like this. So it works well. So the pros, it's built on a well-known NAT64. NAT64, just explain it, it's not that hard to understand. You embed the IPv4 address in the IPv6 address, and then you sort of unwrap it on your way back. It also supports IPv4 literals, which in that case, I said, hey, I got an address from a web server, I did a DNS query, I got an IPv4 address, but if I was just manually configured with an IPv4 address literal, it still works. All right, that's a pretty good pro, and it's well enough understood that it's built into Android devices. I use Android. If I put my phone on an IPv6 only network, and I'm trying to reach, and I've got an app on here that is IPv4 only, my phone is going to translate that IPv4 packet in the phone to an IPv6 packet and send it out through the network to get wherever it's going. And there should be a translator someplace. If I need to get to someplace that's IPv4 only and I'm on an IPv6 network, there's going to be a translator that's going to allow me to do that. I've done some research in the distant past where it seems to me that there's a little bit of additional latency on on Android devices connected to IPv6 only networks because you're doing that CLAT function. that home gateway function is in software on the handset, not in hardware. So so every packet's being rewritten in software. You're adding a couple of milliseconds of latency. Apple doesn't do this. Apple just says, hey, any device in the Apple Store has to support IPv6, using NAT64. It's required to. They don't test everything, but they require you when you're submitting an app to the App Store to check a box saying, yes, I've tested this with NAT64. I've heard that the next generation of Windows is going to include a CLAT on it as well, so that if you needed to, I'm seeing an aggressive nod way in the back, so that if you have a v4 expecting app on Windows, it'll do that translation in that box before sending it out to an IPv6 only network. I mean, that's pretty cool. We're getting there. We're getting to the point where IPv6 only is pretty significantly viable. That's great. Cons to 464 XLAT, it does require the CPE to be able to translate from IPv4 to IPv6. So that means that if you don't control your CPE, if your home users, if you're a residential ISP and your home users are buying their own routers, you're not going to be able to use 464 XLAT as your transition mechanism. There's ways around that, but they're all business solutions, not technology solutions. I have talked about putting that XLAT, that CLAT mechanism in the provider edge equipment, the BRAS, I guess, or CMTS. You're keeping a lot of state information in an edge device where you may not want to keep that much information, never actually implemented it. If that seems like the best solution, well, we know where to go. We know who to go beat up and say we can do it that way. Or you could potentially tunnel from there to someplace that can do the translation in the network. But then I feel like you're adding additional complexity. I also mentioned that there's no redundancy. You can have that well-known prefix be your device, but there's no failover if that box should shut down. All sessions will have to restart. So there are ways to share state between boxes, but I don't think they're standardized. So if you were using, let's say, a firewall as a NAT64 translator, just like if you were using a firewall as a NAT44 translator, but you wanted to have multiple firewalls to do that, some firewalls will allow you to put them in cluster mode, to cluster them so they will exchange state information, so that if return traffic comes across the other firewall, it actually has the mapping to do that, the forwarding. Same works with NAT64. If you can put them in cluster mode, and you kind of want them to be kind of right next to each other, so that all that state information is not going across your backbone, because that's potentially a lot of information. So that may or may not solve your high availability problem. That said, it works. Don't be afraid of it. Another way to do it is with MAP-T. So I mentioned lots of carriers are using 464 XLAT because it matches their mobile networks, and so they already understand it. There are a couple of carriers, including millions of residential users, already using MAP-T. So also viable and scalable, and we know it works. So here I've got, what have I got? A couple of homes, and I'm going to, so I've got a controller. I've got a MAP-T border relay controller server out in my ISP network that tells, as they're discovering their network configuration information, that tells each home, so the server on the right is going to tell the home on the left, you can use this IP address, 203.0.113. You can tell I spend so much time in IPv6, I stumble over dots instead of colons. You can use 203.0.113.225 ports 2001 through 2500 for the outside of your NAT. So now I'm actually assigning, instead of assigning an IP address to the outside to a home, like I normally do, I'm assigning a fraction of an IP address. An IP address and a select range of TCP of ports, not just TCP ports, a select range of ports. So it tells the home on the left, you can use ports 2001 through 2500. It tells the home on the right, you can use ports 2501 through 3000. That way, the device there is actually able to configure its IPv4 addresses. Here we go. So now I've got a device that's going to, in the home, sending a packet sourced from that device 192.168.1.5, port 5678, to a web server, 2003.0.113.33, port 80. Apparently it's an HTTP server, not HTTPS. So we're sending it to port 80. home router receives that exact packet and then has to do a translation. And so it's going to translate it to, this looks just like IPv4, right? It's going to translate it to one of the ports to its outside address, to the 203.0.113.225, as assigned by the controller up in the right, port 2222, which is within the range 2001 to 2500. And the destination address and port stay the same. So I'm building just like the NAT that I went through before, except now I'm going to add a layer. So that was traditional NAT 4.4. Now I'm going to add a layer and say, okay, I'm embedding that information in an IPv6 address. So I'm going to forward from my IPv6 address, 2001:db8:1111:11, and then that IPv4 address, that port number, 2222. That's my source. So when I receive packets addressed to that address, I know I know where to forward it inside my network. And just use, the destination address is similar to 464 XLAT. The destination address is a configured port on the BR, the border relay translator, with the destination IP address and port configured, embedded in the IPv6 packet. Translator receives that and says, oh, okay, I know where this is going on IPv4 because I can read the embedded address at the tail end of the packet. It's going to 203.0.113.33:80. And I know that when I receive traffic back, it's going to go to 203.0.113.225 port 2222. So that's easy. I'm rewriting the headers using the information. I'm rewriting the IP headers to IPv4 using information from the IPv6 headers. So translate it to source address 203.0.113.225 outside of the BR, port 222, and destination 203.0.113.33 port 80. That receives it, says this is just an IPv4 packet, I know what to do with this, and sends it back. What's cool about this, so you receive the reply, based on that reply, source address of the web server, embed that back in the IPv6 address, destination, that IPv4 address and range assigned to that home, easy rewrite to IPv6, so we translate it to IPv6, and it gets forwarded, and we do the reverse translation. The nice thing about this is building a simple IPv4 rule, right? It looks just like a NAT rule. The nice thing about this is it can be distributed. You're giving a lot of the translation load gets assigned to the CPE rather than the big box in the sky. So you don't have to build out enormous servers to handle the load here. It does scale very well. Like I said, there are ISPs in major countries that have millions of users already using this. And if you don't know who, that's because it's working so transparently that nobody knows it. It's also really cool because there's no state information in that border relay, right? The CPE does have a state table, but it's exactly the same state table as you have in IPv4. It's just a NAT table. In IPv6, but there's no state table out in the cloud, which means you don't have all that big complicated information, which allows you the redundancy to say, I don't need to know I don't need to create state so that when I get a return packet, I know where to forward it. I just know that based on the information embedded in the packet. You can also do, this one's a little complicated. You can create domains within your network so that you can say, I've got a data center with a known prefix, and I know how to, and so I can create different rules within those domains. This is kind of the downside of MAPT. And by the way, I was showing MAPT, which is translation, where you're translating IPv4 to IPv6 in the packets. There's also a MAP-E, which is encapsulation, which is doing a very, very similar mechanism, except it's embedding, it's a tunnel. So you're just embedding the IPv4 packet in a tunnel, it gets sent to a BR, it strips off the v6 header and forwards it. MAP-T, MAP-E, I've seen MAP-T at scale, I haven't seen MAP-E at scale, it should scale almost as well. It doesn't allow these special custom domain rules. The other con, so the con is when you look at it, when you start to figure out how to provision this, how do you tell the server, how do you assign the addresses and fractions and sets of port numbers to individual homes, the way they do that is a little bit complicated. And so you really, when you look at the documentation, you're gonna have to sit and stare at it for a while in order to really get it. But once it's configured, but there are tools that help you do that. And once you've got it, the servers just work and let them go. The other con is exactly the same as in 464 XLAT, which is you have to have CPE support. You have to have home gateways that know how to do this. There are ways to motivate users to use your CPE or CPE that you know works, and you can apply any of those that you might want to, but it's the same thing. There isn't a perfect way to do just NAT6.4 in your ISP network. If there were, we would probably do that and not require CPE support. The problem is, as I said before, all of those IoT devices that only speak IPv4 in the home, we have to find a way to get them across our v6 only network to something that can translate them back to IPv4. So that's why CPE support is required in both of those. One more transition mechanism, and that is the kind of thing if you're running a data center and you want to go v6 only inside your data center, why not? But still want to be able to support IPv4 because, let's face it, the entire internet is not running IPv6. So this one's called SIITDC, or Stateless IP ICMP translation for data centers. Sometimes the IETF is not the best at setting up acronyms. SIITDC. So we've got a device out on the internet that's IPv4 only. It wants to reach some server inside your data center. It sends a packet to the outside of your translator. So in this case, I've got a device, 192.0.2.50, sending to 203.0.113.1. You'll notice that this translator actually has the entire /24 configured on it because it can translate for lots of devices inside the data center. It sees this packet and says, okay, you've seen this mechanism before. I'm going to take that IP address, and I know which server in my data center that means. I'm going to forward it to destination 2001 DBA F002:1:80, which is the server on the top, with a source address, my IPv6 address, plus the IPv4 address that the original packet came from. That's how I'll know when I receive the response where to forward it back out. Again, all the information is embedded. You don't need a state table, so it's very scalable. And this is how some of our favorite organizations that are using v6 only in their data centers or in their application servers, that's how they're doing it, and it scales amazingly well. Pros, stateless, so scales well and supports redundancy because you don't have to, because any server that's configured to handle that just uses the information in the packet to do the translation. It does enable the pro is enable single stack with the data center. Boy, if you can narrow it down, so you've got, especially if you have a large data center, if you can narrow it down so you're only running a single address family, life gets a lot easier. There are also some clever things you could get into if you're the size organization that gets to write custom stacks and custom applications, and you've got 18 quintillion bits to work with in a host address. Lots of interesting things you can do with your containers and moving things around. It is also great because it allows incremental deployment. You don't have to roll this out everywhere. You can do a single server's IPv6 only, and this applies to the translator is only configured to forward to that server. And then as you sort of roll out other servers to IPv6, it just sort of scales out that way. You can do load balancing, just split the addresses among multiple translators, and the IPv4 address is preserved, which means if you're doing forensics later, or if you get lawful order, you can look at the logs and say, well, here you go. This is the IPv4 address that was hitting us. Pretty handy. You can even do geolocation with that, right? Cons, well, it does require a transition to IPv6 because it's using IPv6 only on the server. I'm not sure that's a con, but it doesn't work if you're not using IPv6. And your address parsing systems. I mentioned at the bottom there, you've got the address, the IPv4 address is preserved, so you can do discovery and forensics using that IPv4 address. But you may need to touch your parsing systems in order to understand how to search for that. It's probably just a regex, but also if you're storing addresses in some logging server someplace, you have to pay attention to it's not just a 32-bit address anymore, it's a 128-bit address. You need all those addresses, but it may also depend on what context you're looking for, whether you're storing 128-bit objects or 64 bits and another 64 bits, or sort of how you're doing your logging there. Depends on what your application is. Just a little more to think about. We're getting there. I mentioned I was going to give you a handout. Didn't do a handout. So obviously, the slides are available on the agenda. So if you go to the NANOG agenda, NANOG 92, look for the Wednesday morning session, IPv6 familiarity training. Click on that. There's a PDF there. That's exactly these slides. So you can download these slides and see this recommended reading. I will say that when I started to look at IPv6 seriously and say we need to figure out how to deploy IPv6, I need to get smart enough on IPv6 to begin to lead a program in a large network to deploy IPv6, where do I start? So I started with RFC 4291, the IPv6 address architecture, which is simply the things that I talked about at the beginning, 2001:DB8, 2001:0DB8 truncates to 2001:DB8. I forgot to mention, we mostly use lowercase letters in when hexadecimal, just because it's easier to not get them confused. It sounds like you're shouting your address if you use uppercase letters, but it's not wrong. The use of : the address architecture is there. It's a pretty straightforward, simple to read RFC. Neighbor discovery. It's a really good one for understanding the mechanics of neighbor discovery protocol, the router advertisements. There's a whole section in there about the packet headers and formatting. It's a long part of that RFC. It's okay to skip that if you don't need to know that information. If you're looking in Wireshark and you need to be able to parse the headers, you probably need to read that. If you're just trying to configure your devices, skip that part. You don't need it. RFC 4862 is how to use SLAAC. 8106 took us a ridiculously long time to be able to provision DNS servers, to be able to tell if you've got a router, if you're a router and you're telling a network about, here's this /64, this 48 you can use in this network, go ahead and send yourself an address. The host in the network would still say, okay, what DNS server should I use? So you still needed to use DHCP for a long time. Took us a long time to be able to push an option in there for DNS, reverse DNS, and I forgot what the other thing I was going to say was. The RFC on DHCP v6. I don't know if you need to know this. If you use DHCP, you probably want to know as much about DHCP v6 as DHCP, just so you can see the comparable options there. I'm not sure I said before, there's IANA and IAPD. IANA is network attachment, I think it is, a network association. That's a single address. So here you go, here's an address. IAPD is a prefix delegation. So here you go, router, here's a 64 or a 56 or a 48. So that's the difference there. So whether you're requesting a single address or a prefix, that's the only difference between IANA and IAPD. So it's different and useful in that way in DHCP v6. I mentioned path MTU discovery, probably a good one to know. If you read all these, especially if you skip the sections or skim the sections that you don't need, 2 or 3 hours, maybe it's 4 hours of reading, and then you know a lot about IPv6. You understand the mechanics really, really well with just a couple of hours of the details. You know how IPv6 works. For extra credit, I referred to some of these. There's a lot of RFCs now. Obviously, I'm a big fan of using RFCs to understand technology. So these are good ones. The network scanning, when I was talking about how the huge number of addresses doesn't protect you against network scanning, that's the RFC that talks about it. Actually, those two, and then the fragmentation was kind of an important one that I mentioned there, where you need to make sure that you're allowing packets too big and protecting the potential neighbor discovery vulnerabilities, potential attack surface. Transition technologies, obviously I mentioned these, and there's two, I guess, on MAP-T and MAP-E. They're pretty good. When you're getting to this point, you're starting to get to where maybe this is where the vendor documentation will be as good as the RFC in order to understand what you're trying to accomplish. I thought I had one more slide, so I've left plenty of time for questions. I do encourage you, I love to talk about IPv6. Happy to talk about IPv4. I encourage everybody, I've included my email address here, my LinkedIn profile, connect. want to talk about it more, I'm happy to take questions now. I'd love to take questions now, but I'd also love to connect one-on-one. Sometimes people don't like to get up to the mic and ask questions. Everybody knows everything about IPv6. I did complete training.
Thank you again.
Sorry. I'll stand up for a second. Doug Kaveen, CCSI. Lee, I just want to say that was great. I think it was a great run through. I appreciate you taking the time to do it here at NANOG. And, you know I gained a lot from it, and I hope everybody else here in the room did too.
Excellent. I'm certainly also available to do this again, other venues, let me know.
Hey Lee, great session. It's me, Farouk from Consulting. I do have a question, like, this IPv6 data center only. Is this transition make things slow where you have a hyperscale data center, like you transition from IP4 to IP6? And
So there's a presentation yesterday that was Meta talking about how they removed IPv4 from their network. And so it was a very similar architecture to the SIIT-DC. And so he goes into more detail about sort of what they did and how they're doing the translation, and then some of the hurdles that they ran into. I really recommend that one for a hyperscale data center, because absolutely, if Meta can do it, probably any data center can manage it. But he also talks about some of them, like, here are the hurdles that we ran into, and we had some vendor problems, and a couple of sort of, hey, we didn't realize this was a best practice until we ran into this problem, and here's what we had to do.
got it.
Did I answer the question? I'm not sure I got
Yes,
that.
yes.
Okay.
The second question I have, like, I know we know all this IPv4 subnetting and subnetting calculator, and there are many tools there. Do we really need this kind of tool for IPv6 where we designing /64 and, the large network, our enterprise network, where we can use some calculator tools?
So I love this question. So I have at previous NANOGs, I've given out glasses that had the IPv4 CIDR table on them, and I call them CIDR glasses. My business card has an IPv4 CIDR table on the back of it, so that you can see how many IP addresses are in a /29, a /27, a /23, and so yeah, I really need that in IPv4. In IPv6, and if I'm going to configure a /27 or a /21 in the middle of a network, a larger supernet, I really need a tool to tell me what's the network number, what's the broadcast number, so what's my usable range. I need that in IPv4. Once you get used to the nibble boundaries, the /64, /60, 56, 52, 48, once you get used to that, you're used to it, you don't need a calculator anymore.
Thank you.
And I will say, I found, and doing other training, I have found that it is the hardest part. Getting used to that, it takes a lot of iteration and playing with subnetting and doing address plans, and sort of once you've seen it a few times, and it may be a few dozen times, but once you've seen it, you start to get used to those numbers and you go, this actually is way easier than IPv4 because I don't have to go figure out what number between 0 and 255 is the network number. I know it's the number after the colon.
Thank you.
Absolutely, thank you.
Hello, I have a question. Oh gosh. In a hypothetical situation, say like if someone's running a web server and then they're taking actions based on the incoming v4 address as a header of some kind, and then because for mobile, I do see that there's IPv6 and 4. In this case, with a web service, need to consider anything for the incoming IPv6 address?
Yeah, I'm going to try and answer that question, but I'm also going to touch on something else with dual stack. So yes, if you are running a web server that is dual stack, then you're going to need to be able to log both IPv4 and IPv6 addresses. Your parsing systems will need, your logging systems, your log parsing systems, whatever tools you're using to capture that information or search that information or graph that information will need to be able to do both. And if you're looking at individual addresses, you're probably going to be okay. Just, hey, this is how much traffic we're getting per address. That might be fine because it's just per address, but the libraries are a little bit more complicated. But the other, and I didn't put this in here, but the other big mistake that I see a lot of people doing in their v6 rollouts, this is tangential to what you asked, but is hey, I'm monitoring my web server right now. If the web server goes down, I get an alert and I got to go panic. But if I'm monitoring by name, www.example.com, and the IPv4 address goes down, but the IPv6 address is still up, I might not get an alert, or vice versa. So now you need to monitor both the name, so you know if there's a DNS problem, and the IPv4 address and the IPv6 address if you're running a dual stack server. So pay attention to both. Did I answer the question though? I think I lost you a little bit partway through the question.
I guess specifically, say like with the web, like if you're running a web service at the moment, if you're only configured for IPv4, do you have to do anything to take anything into consideration if the phones are already doing IPv6, for example?
Okay, thank you. Thanks for repeating that. So if you're running an IPv4 only web server, do you have to worry about anything that's doing IPv6? The general consensus has been, and this is sort of standard internet architecture, I only have to worry about my network. You have to worry about yours. So if you're a mobile carrier who's rolling out IPv6 only to your mobile users, and they're doing a v6 only, then it's that mobile carrier's problem to get traffic back to me on IPv4. So it's the mobile carrier who's doing 464 XLAT or whatever transition mechanism they're doing. Or maybe they're doing, very common too, IPv6 plus NAT44, or NAT444, depending on topology. So that's fine and that works. So there isn't anything that you need to do there, although there is, because you may be seeing multiple users sharing an IPv4 address on v6, there is a best practice in logging to make sure that you're logging not just the source address, that when you run web server, who's sending GET requests, so I've got a log for who's accessing my server. Best practice is to log the address and the port number, and that is not on by default in either Windows or any Unix that I know of. So it's easily configurable if you go search for it, but it's not on by default. That's the only thing that I can think of for worry if you're operating a web server and aren't doing IPv6 yet.
Thank you.
Evgeny Kasary, Adrix. Lee, great talk. I think things like that truly help us with faster adoption of IPv6. And if you'd look at your magic ball and just speculate, what do you think the adoption of IPv6 will look in 10 years?
So Jeff Houston gave a presentation yesterday looking at, I think he was using Google statistics, and he did a straight line projection. Just if things continue going the way they've been going, it'll be 20 years before you have 100% adoption. I've seen the trouble with doing that kind of projection is when you're projecting the future from the past, how far in the past you use and what assumptions you make about the best fit, what kind of curve is the best fit, makes all the difference in what the projections look like. So Eric Vinke has a site, great guy, has a site that pulls together the statistics from multiple different sources. So he's got Google's numbers and Facebook's numbers and Akamai's numbers, I think, and he'll let you project for any given country, what's your best fit? What curve do you like? How much data in the past did you use? How far forward should you go? Every time I look at it, I think that we get, if I'm just straight lining, I say we get to mid-90s% adoption by 2034, 2035, so it's 10 years. The trouble is, I've been getting the same projects. I've been getting 10 years for the past 20 years. So it's a moving target. Here's the thing. We can't assume it's going to be linear. There's no reason to believe that it's going to continue at the same pace. Most adoption curves are S-curves. There's a slow start. We certainly had a slow start with v6. And there's just a ramp up, and there's a long tail. I don't know when we hit the long tail or what that looks like. I'm going to guess that somewhere around 93%, v6 will slow down, and that last 7% will take many, many years to get to transition and be available over v6. But it may be that at that point, I don't care about the remaining 7%. They can be offline, and I don't have to worry about how I get to them. I don't know. I don't know who's in the long tail. But also, the two sort of laggard spaces that I see are enterprise IT departments. They just have no need to deploy IPv6. They're getting a /29 or whatever from their upstream. Maybe they've got a /24. Maybe they've got a /16. They just are not running out of IPv4 addresses, and they've got so many other things to worry about that they don't see the advantage. There are a few cases where that's not the case. I actually wrote a guest blog for ARIN a few weeks ago where I talk about if you have a /16 and you're an enterprise IT department, that address is worth a couple $1 million. Maybe that you want to move to IPv6 so you can sell that off. So there's some motivation there. But the other laggard space is consumer electronics. And until the consumer electronics widely have IPv6 and we've had a replacement cycle, then we still have to support IPv4, at least in the home. If we were to see a change in the trends for either of those, then that would accelerate the curve significantly. The other thing is that if you look at Jeff Houston's numbers, labs.stats.apnic.net, I think it is, you can, and sort by countries, you'll see that the most populous countries have pretty significant v6 deployment. And so now we're into kind of the law of small numbers, is it takes much more aggressive deployment by much smaller countries in order to move the needle. So there's a little bit of a trade-off there. I think Indonesia and Nigeria are the next two most populous countries that have less than 20% deployment. So if those two countries were to accelerate, we'd see a major change. All of that is to say, hey, it's multivariant. I can't really predict, but if I just straight line, I get fewer years than Jeff, but I keep getting the same number of fewer years than in the past.
Thank you.
Hi, Matheus Pacheco from Triton Digital. Thanks, Lee, again for the presentation. We are kind of crawling, starting on that IPv4, IPv6 migration. And one of the things I'm foreseeing is that we have a lot of resources and a lot of trainings on YouTube, on many of the ARINs, APNICs, everywhere, about implementing, about migrating, about configuring routers and everything. But one thing I'm wondering is we do have that group of system administrators, system network administrators that will be implementing, but we also have a group of juniors or people that will be working directly with it, but not necessarily implementing or doing the changes on the router. And not only those people, but also level 1 support for the products that deal with IPv4 like every day, and they know what it is, they know where to put and understand more or less what they do, right? And I don't see much of resources for that less technical people on introducers. So do you have any recommendations on resources, documentations, training, or whatever for those not that technical folks that we need to handle IPv6?
Sort of level 1 help desk level training. So a couple of thoughts. So when we rolled it out at Time Warner Cable, we were trying to roll out to 1% of our users by World IPv6 launch. And we didn't quite make it, but we in a matter of a week or two, we rolled out to, I think, 100,000 users. And we just kept going, accelerating from there. And so I had a war room where I had a bunch of people in the room on conference calls, making sure that if anything bad happened, is rolling this out on this date, that we would be there and able to jump on any problems that we saw. And what we heard was nothing. And so rolled out to 100,000 users in a week. And we heard, and I kind of was trying to go through my connections and say, what's the help desk reporting? And what I heard back was the help desk is reporting more people calling to order pizza than complaining about IPv6. So it's not a big deal. I would also say most of the help desk techs that I've worked with, and this is both ISP and corporate IT, they're not spending a whole lot of time looking at IP addresses. They're spending a lot of time resetting passwords and rebooting devices, right? That's where they spend 90% of their time. That said, we also worked with Jason Fessler. We were worried about how we do help desk tools, how we're helping people detect things. And he built, I think it's test-ipv6.com, although there's also ipv6test.com, and I can't remember which one is his. But one of the things the tool does is there's an ISP version that will let you detect whether your user is behind a tunnel, whether they're doing NAT, and it'll help the user and the tech do some troubleshooting to figure out like where in the network the problem might be. So that's a pretty good resource. There was a document, it may even have been a BCOP, a best current operating practice, that was IPv6 troubleshooting for help desks. I think that's what we called it. So if you Google that, I think there is a document out there. I'll admit, it may be a little stale. It's been a few years and it may not be comprehensive enough, but then again, if it's not comprehensive enough, it's probably time to escalate to layer 2 or 3. That's my thoughts on that. And you know what? I also sort of would like to dig into that and say, if you're doing, we did training to our help desk, but most of it was relax, don't worry. You might see an address like this. You might see multiple addresses on the interface. It's fine. Everything's working. You might go as far as say, here's how to do traceRT 6 or traceroute 6 instead of traceroute. Even that's changed in the last 10 years. So there may be some few things like that you want to teach the help desk, but generally for layer 1, tier 1 support, you're not even doing dig, right? At that point. That's kind of my thoughts, but there's probably more discussions worthwhile there.
Hi, this is Tao from Canary. So I have two very specific questions. One is, I wish I had this presentation earlier because you mentioned like we reserve like /64 by use /127, but in our network. We reserve /64 and use /64. So do you think it's necessary to ask all our partners, like the BGP peers, to change it to /127?
So that's an excellent, very specific question, and I think my answer is I haven't tested this. That's my answer. But I think my answer is you could change your side to 127. And mitigate your side's the concern on your side from a ping pong attack, and then advise your partners to also change to 127. But even if they don't, you've mitigated your risk. You've advised them to mitigate their risk. But I think the packets will still exchange just fine between mismatched net masks. I think. Haven't tried that. But that's what I would look at. I do think it's a documented best practice to use 127 just to mitigate the neighbor discovery exhaustion risk.
Okay. The second question is, we got on this issue like 6 months ago, and we're appearing with, let's say, Google, and we have a customer is connecting to Google through us. So 6 months ago, we for every customers, we have source IPv6 address filter. So you only need to, your source address only needs to be in this list. So we got this issue like this, one customer, they have, their packet just cannot get through. So at the end, we found that we need to allow FE80 in this list for this customer. I don't even know why we need to allow FE80. So
that's really strange because FE80 is the link local address and it should only ever be used on a layer 2 network. I can't imagine why that would legitimately be needed for inter-AS traffic. I don't think I have an answer for you. That's a good one.
Okay, all right, thanks.
If anybody has thoughts on that though, like we've got a few more minutes, check me on time, Adair. Are we okay? We got 3 minutes. So if anybody has thoughts, then find him or jump to the mic.
Hi, Dennis Lundstrom with the House of Commons Canada. Do you have any tips and tricks, pinpointers or resources for ramping up IPv6 awareness predominantly for an enterprise network engineering team from the perspective of operations?
Oh gosh, so many. I did some research with Jesse Soul years ago about what helped promote IPv6 adoption, and we looked at 15 different things that different people had done and what worked. And we found things like network government mandates, no effect. In fact, a few years ago, if there was a government mandate for IPv6, there was less IPv6 than if there was no mandate. We found that public-private partnerships, where for instance, in Slovenia and Belgium, the government convened network operators and said, so here's our problem. We're worried about NAT44. We're worried about not being able to find bad guys because there's address sharing. What do we do about that? And they talked together and said, okay, we're going to do IPv6, and started asking everybody in the room, so what's your IPv6 plan? And when the CEOs of the major networks say, we don't have one, they say, okay, we're going to reconvene in 6 months and we're going to ask you the same question. And they come back in 6 months and the CEOs start to be embarrassed that they have nothing to say. So they start to ask their teams, what's our plan? How do we get there? So that is an effective thing. That's something that partnership where it's really just bringing the community together to discuss what we're going to do and how. That can be effective. The most effective that we found, though, was every place we looked that had high v6 deployment, there was a champion. There was one person who was technical and was high enough up in an organization who just decided, we're going to do IPv6, and that person made it happen. They didn't do it alone, it wasn't just them, but there was always one person who became the evangelist within an organization, within a network to do it. For enterprise, I don't have a lot to say, and I think there's a lot more to be said.
Yeah, the problem is essentially, from an architecture perspective, there's a lot of great resources, there's RFCs, but if you have that type of heavy reading and hand that off to an operations team that does your day-to-day operations, they don't have time to get to that depth. So they're never actually going to get to that day-to-day operations in IPv6. And it's like, how do you get there?
In the US, NIST has some great guidelines for enterprises. There is an RFC for enterprise deployment guidelines. I'm still working on some new tools and references to make it easier for network administrators, but they're still looking at the incentives. And I don't know if that's a birds of a feather session we need to have. We probably need to have a larger conversation, or even better, reconvene in a place where there are enterprise IT directors, not ISPs and data centers. This may not be the right place to go there. I would love to talk about that in great detail. Adair's about to play me off.
Yeah, I feel like that it's a little bit of a gap, and there's also an opportunity to maybe address that gap and build some bridges.
Yes.
Thanks.
Okay. Sorry, I am not kicking everybody out of this room. One of the reasons that Lee is such a widely respected and highly regarded presenter within the NANOG world is that he will talk about IP addresses until we close the room. But it is Wednesday, and Wednesday is kind of a weird day for NANOG. Just a reminder that lunch is on your own today. There are a number of restaurants around here where you can go get some food. There's a bar in the lobby, but it is your problem. Please don't forget to complete our NANOG surveys. You'll find all the meeting surveys at nanog.org/surveys. And if you have a presentation idea for a future NANOG conference, you can submit it now for NANOG 93 in Atlanta. Our spotlight topic for Atlanta is automation. We are not restricting topics to only automation, but we are hoping to kind of spotlight automation at that conference. We are back from our lunch break at 1:30 p.m. And now I am going to let Lee do what he does best and keep talking and talking and talking about IPv6 addresses.
Thanks.
So Doug, CCSI again. Actually, the gentleman before me asked most of my question, which was about enterprise adoption and what are the incentives and how do we build those. So I would also love to have a conversation because I do have access to pools of enterprise customers in certain spaces.
So, okay, we're officially closed, everybody's excused. You can go find lunch, that's all right. But now that we're closed, I'm going to spend a little bit more time talking about that. I think that there has been an incentive mismatch, and that's been part of our problem. I know of a couple of folks, and I don't want to go plugging companies and services, but I do know of several folks who are working on, again, making it easier, providing tools and resources so that it's easier for enterprise IT folks to deploy IPv6. Not that it's hard, it's just, it's always number 5 on the list of things to do, and they're only going to get 3 done this year. And the next year's goals, they're only going to get 3 done, it's still number 5. They've had some problems. When I was in corporate IT, I was looking at the firewall documentation we were using, and I went, okay, let's just make sure that if we were to, that it'll block IPv6 packets. And I went, okay, so here's all the rules. And I got to the bottom, and it said, we don't inspect IPv6 packets. And I went, you mean you forward IPv6? Yes, the firewall forwarded IPv6 uninspected. That firewall is end of life, and so the next generation presumably is doing at least basic inspection. But there's stuff like that that we have to pay a little bit of attention to. I do think that in the US, NIST has done some great work in providing documentation for how to do it, but that's still, although NIST documents tend to be comprehensive and therefore long, but it doesn't address the incentives. And I think the incentives turn out to be things like either I can make money by selling addresses, I can save money because I don't have to pay my hosting provider, my access provider for static addresses, I don't have to pay my cloud company for static addresses. So there may be cost savings in there, but we sort of, if it's not one of those two, then we get into, all right, what are the magic things that you can do with IPv6? One other thought on enterprise, there was a guy at RIPE many years ago who was at a bank, Rabobank, and he said he was put in charge of assessing their IPv6 plan, and he said, we don't have one, we don't need one. And then he went, all right, but my boss told me to do this, so I'm going to go check with the other teams and say, do we need an IPv6 plan? And this is at a bank, so it's an enterprise, you know, and the network is not their basic function. So he went around the department and said, do you need IPv6? Every department, and said, do you need IPv6? And every department said, no. And he said, when do you think you might need IPv6? And they all said, I don't know, 5 years at the soonest. Okay, so 5 years at the soonest, how long will it take you to roll out IPv6? 7 to 9 years. Oh, okay. When do you think there might be an application or a service or a tool or something that requires IPv6 to work or to work effectively, and it was all, you know, not for 5 to 7 years. Okay, how much notice will you have that there's this thing that means you need IPv6? 12 to 18 months? Okay, so sometime in the next 5 to 10 years, you'll get a year and a half of warning that you need to deploy IPv6, and it'll take you 5 years to deploy IPv6. All right, right there, you're doing a little bit of risk mitigation on the future to say, I don't know why we need IPv6. I don't need to rush, but I need to make sure that if I ever do need it in the future, I can get there in time for whatever my need is. That's sort of my business case for IT.